In Chapter 14 of the Seaborg text, we're going to introduce some new mathematical tools that we can use to analyze the stability of feedback control loops and that we can use to aid us in control loop design. These new mathematical tools are based on what we call the frequency response of the feedback control loop. Consider a first-order process with a sinusoidal input forcing function. You may recall from Chapter 5 that we've already seen what the output of a first-order process with a sinusoidal input looks like. After some exponential terms decay, the output of this first-order transfer function with a sinusoidal input will be a sustained oscillation. Here we're indicating the output perturbation with a subscript L to indicate that this is at a long time after the exponential terms have decayed. This sustained oscillation is characterized by three parameters: an amplitude that we call A hat, a frequency that we call omega, and a phase angle that we call phi. The amplitude of this perturbation oscillation in the output variable is proportional to the gain of the transfer function and the amplitude of the sine input, divided by the square root omega squared tau squared plus 1. The frequency of the sustained oscillation is equal to the frequency of the input forcing function. And the phase angle describes how much out of phase the output is from the input forcing function. And that phase angle is minus the arctangent of omega tau. To understand this in the context of a physical model, let's consider this surge tank with gravity-driven flow out of the tank. We've already performed the material balance on a surge tank like this, and we found out that the level in the tank is related to the inlet flow rate according to a first-order transfer function, and that the outlet flow rate is also related to the inlet flow rate according to a first-order transfer function. Now let's suppose that our inlet flow rate is varying sinusoidally in time with a frequency omega and an amplitude A. When that inlet perturbation begins, it will cause a perturbation in the outlet stream flow rate that will include some exponentially decaying terms and then sustained sinusoidal oscillations with a frequency omega equal to the frequency of the deviation in the inlet flow rate, but shifted in time by a phase angle phi. The oscillation in the outlet flow rate will have an amplitude that's proportional to the amplitude of the oscillation of the inlet flow rate. If the frequency of the oscillation describing the inlet flow rate perturbation is very low, that is, it's oscillating very slowly, then omega is very small and the phase angle goes to zero. Note that when the frequency omega goes to zero, the phase angle also goes to zero. Furthermore, since the gain of this transfer function is 1, when omega goes to zero, the output amplitude A hat matches the input amplitude A. Therefore, the input matches the output. However, as the frequency gets very large, that is, if the input flow rate is oscillating very quickly, then the output amplitude A hat gets very small, and in the limit as the frequency goes to infinity, the output amplitude A hat goes to 0. And in that same limit, the phase angle goes to pi over 2. That is, the oscillations in the outlet flow rate are 90 degrees out of phase with the oscillations of the input flow rate. In this case, we say that the oscillations are damped because their amplitude is smaller than the input amplitude, A. Without testing sinusoidal inputs of various amplitudes and frequencies, what we can say from the frequency response analysis of this first-order process is that for very low frequency oscillations in the inlet flow rate, the outlet flow rate will match the inlet flow rate perturbation. On the other hand, for very high frequency inlet perturbations, the outlet perturbation will go to 0 in the limit as the frequency approaches infinity. These two asymptotic limits, that is the low frequency limit and the high frequency limit of the frequency response for transfer functions, are important indicators of the transfer function behavior and stability. We can find the frequency response for any stable process in the Laplace domain by substituting s equals j omega into the transfer function g of s. Recall that we said that the frequency response of a transfer function is characterized by three parameters: the amplitude of the oscillations, the frequency of the oscillations, and the phase angle with respect to the input function, where the input function is a sinusoidal oscillation. We also found that the output frequency will be equal to the input frequency omega. Therefore, we will characterize the frequency response of any transfer function as the amplitude and phase angle of the output as a function of the input frequency after all of the exponentials decay. Now, for any stable process, by definition, the exponentials must decay instead of grow with time. So the frequency response must be described by substituting s equals j omega into the transfer function g of s, because the result then will give us sustained oscillations. And omega is the frequency of our input forcing function. Of course, when we substitute s equals j omega, where j is the square root of -1, into our transfer function, then the transfer function is likely going to have both a real part and an imaginary part. We'll call the real part r and the imaginary part I. Often we have s's in the denominator of transfer functions, and that's okay. If we have j's in the denominator, then we simply multiply the numerator and denominator by the complex conjugate of the denominator, and that will give us transfer function in the form g of j omega equals r of omega plus j times I of omega. The resulting sustained output oscillations will have an amplitude that we call a hat, a frequency that's equal to the frequency we selected for our input forcing function, and a phase angle, where a hat is the square root of the real part squared plus the imaginary part squared multiplied by the amplitude of our input forcing function, and the phase angle is equal to the arctangent of the imaginary part divided by the real part. Now, because our amplitude of our input is arbitrary, we'll define the amplitude ratio as the absolute value of a hat divided by a, that is the output amplitude divided by the input amplitude, and that will be the square root of r squared plus I squared. We will also define the normalized amplitude ratio as the amplitude ratio divided by the gain of the transfer function g, or AR divided by k. If we plot the imaginary and real parts of g on the complex plane, then the amplitude a hat is the distance from the origin, and the phase angle phi is the angle that that line makes with the real axis. In the next video, we'll try this method. That is, we'll substitute s equals j omega into different types of transfer functions to see what the frequency response looks like. That is, what the amplitude and phase angle look like for different values of the forcing function frequency omega. We'll begin with a transfer function that we already know the answer to, the first order transfer function.